Okay, in order to characterize electricity, we need some terminology and we need to understand the relationship between those terms. In this case, voltage, current, and resistance. And we'll finish up talking about two different types of electrical current. First off, what's a circuit? When I hear circuit, I think circle. I've got a circle. Okay, it's a square here, but it's a path that we can get back to home on, right? We've got a power source. Whatever that may be, that is voltage. Then we have a wire connecting that power source to a load. Here we've got a light bulb. The load has some resistance in it. And then from that load, there's a return path back to the power source, completing the circle or circuit, if you will. All circuits are going to have voltage, current, and resistance in them. The power source is the voltage. The wires or conductors that complete the circuit allow the current to flow from the power source to the load. And then the resistance of the load is what causes work to happen. The light bulb lights up because of the resistance. And then we have the return conductors back to the power source themselves. Okay, let's start off with voltage, or volts. You'll see it abbreviated with a V. That makes sense. Sometimes you'll see an E for the electromotive force of the electricity. So if you see your V or an E, think of voltage. It's the measurement of electrical pressure or potential, that electromotive force, as I said. And often when we talk about electricity, we're going to use a water analogy. And this potential difference, this electrical pressure or potential, is kind of like water pressure. Imagine two tanks of water. They're connected together with a pipe between them at the base. There's a valve in there that's closed, so the water's not moving between them. But one tank's fuller than the other. What's going to happen if I open that valve? Well, there's more pressure or potential difference on one side than the other, the more full side as compared to the less full side. So that pressure, when the valve is open, is going to cause flow to happen between the tanks. Eventually they'll level out and the analogy breaks down there, but that's the idea here. Voltage is like pressure. So the electrical concept would be that potential difference, which is our voltage, the pressure, is present to push electrons, if you will. Here I've got a PV module. It's 17 volts. It's charging a 12-volt battery. That 5 volts of difference is what allows the PV module to push electrons into the battery. If they were both 12 volts, there's no pressure difference, there's no voltage difference, there's no potential difference, there's no current that's going to flow. We need that higher voltage to be able to push into that lower voltage. So the water analogy there works pretty well for voltage. It also works pretty well for current or amperage, as we'll see here in a second. So amps, A, or I. Again, you'll see this other abbreviation for it sometimes. I meaning current or amperage. It's the intensity of the flow of electrons. That's where the I comes from. So the rate of the flow or the intensity. So A or I, amps, current, amperage. You'll see them used interchangeably. Don't get too hung up on that right now. Sometimes one is more correct than the other. Sometimes I get them wrong. As long as you understand we're talking about the rate of flow, then it's not going to be a problem. The water analogy would be gallons per minute or liters per minute, whatever your flavor is. How much is flowing? What's that flow rate, right? The electrical analogy would be how many electrons are flowing. Right? What's our current flow? What's the intensity of the flow, right? Depending on the power source, it may be really high. It may not be that high. It depends on what the load is. There's a lot of different factors that go into play there, but the flow rate in amps is the electrical concept here. The final term we want to hit on is resistance. Resistance, ohms. So our symbol for ohms, or R, you'll also see that for resistance. And this is the opposition to electrical current. It's kind of like electrical friction. And what it depends on, the abbreviation of the mnemonic device is MALT. The material of the conductor. What kind of wire am I using? The area. How big is the wire? Right? The bigger the wire, the less resistance it's going to have. How long is the wire? If I got to go a long way, there's going to be more resistance. And then materials, temperature causes different things to happen. Temperature goes up, resistance goes up. So the temperature is going to have an issue, have an effect as well. Much like current, and voltage, we can use the water analogy. So friction, the opposition to flow, right? Depending on the size of my pipe or my hose, I'm going to get a different amount of flow. Here I've got a smaller hose, more friction, less water flow. The electrical concept, the opposition to flow, is resistance. And in this case, we've got our PV module connected to a battery on the right there. We're charging the battery. We've got a bigger wire, and it's shorter. We're going to have less resistance as opposed to the smaller, longer wire on the bottom, right? Remember, malt, material, length, area, temperature. If everything else is equal in these two scenarios here, the one on the top with the bigger, shorter wire, there's going to be less overall resistance to the flow of current. Now, the way these terms are related, this is Ohm's law, voltage, current, and resistance, and we can use this handy triangle to give us a spatial representation of how these terms are related. So the first off is volts equals current times resistance. The way you use the triangle is cover up the term you're solving for, and then use the spatial relationship of the two uncovered terms to provide you with the equation. So if I cover up the V, I've got an I next to an R. V, which I'm solving for, equals I next to R, I times R. So volts equals current times resistance. What if we want to figure out the current? Cover up I, and I have V over R left over. So I equals volts divided by resistance. And then the same thing for resistance. If I'm solving for R, cover it up. I've got a V over an I left over. V divided by I. Resistance equals volts divided by amps. So that's an easy way to remember the relationship between these. If you remember the Ohm's law triangle, it'll make it so that you can solve any of these anytime you may run into some math requiring you to solve for one of these terms. Okay, so what about types of electrical current? We talked about voltage, current, and resistance. We want to break current down into two subcategories. First is alternating current. Alternating as in back and forth, the two-way movement of a charge. And this is the type of current that is produced by spinning turbines, electrical generators, AC generators. They create what is called a sine wave. A sine wave. So that spinning action in the electromagnetic induction creates this sine wave where we build a voltage and then it drops and it switches directions and we have voltage down here and then it goes back again and on it goes. That's our AC sine wave. One of those cycles starting at zero, going to a positive voltage, back to zero, down to a negative voltage and back. That's what we would call one cycle. One cycle. 50 hertz, 60 hertz, different parts of the world have different cycles for their electricity, but that would be one cycle there. So we're really showing 1.5 cycles in the total graph. The other type of electrical current is DC current. This is the one-way movement of electrons, or one-way charge movement. In this case, this would be the type of electricity that's generated by a PV module. That's one of the sources of DC current that's out there. And as you can see, it's just constant. It's a constant voltage, always going in one direction. There's no back and forth and up and down going on here. The one-way charge movement. So key points about the characteristics of electricity: voltage, current, and resistance are fundamental concepts of all electrical circuits. Volts, or V or E, is pressure. Current, A or I, is flow. And resistance, Ohm symbol, or R, is the opposition to flow. Remember your Ohm's law triangle to describe their mathematical relationship, and recall that there's two types of current: AC, alternating current; DC, direct current. Alternating current is what comes out of the plug in your house. Most of the electricity that we use from and that is provided by the utility grid certainly is alternating current, but there's lots of sources of direct current out there as well, and many of our renewable energy systems use both types.